Hello, welcome to physics class on alternating current part 4. In the previous part we have done the topics that were struck through, and this number 10 wattless current, this has been deleted from the syllabus, and so for today we will try to do oscillations. Okay, what type of oscillations? LC oscillations. And then we will try to continue with AC generator, and in the last part we will discuss about the transformer, but not in this part, it will be in the part 5. Now let's directly switch on to that of LC oscillation. In this LC oscillation, it is nothing but this is a simple combination of L and C in parallel. So this is the inductor, okay, it has been connected with the capacitor in parallel. What happens when this capacitor is fully charged, and if it is connected to an inductor, then this capacitor will try to discharge current through the inductor, and at the same time when it is fully discharged, then what happens, it will be charging again this capacitor, and in that, if it is fully charged again, then this side will be positive and this side will be negative again in that case, just like this, but the polarity will be opposite. And again, what happened, the fully charged positive side, from this positive side current will be again discharging through the inductor, and it will keep on oscillating like this. Got it? That process of oscillation, we call it that as LC oscillation. Now in order to know further how this fully charged capacitor will be connected to this inductor, the circuit diagram may be drawn like this. Suppose if the inductor is here like this, then this circuit may be drawn like this. The inductor may be here like this, and the capacitor parallel to this inductor, it may be connected in this way, and to the source of EMF, it will be connected from here. Now let's take it that this is the positive terminal of the battery, negative, negative, positive, negative, like that. It will be connected here like this, and two keys will be used. The first one, let's take it as K1 and this as K2. This will be capacitor C, and this is the inductor L. So what happened, this is a positive of that battery and this side is negative. So what happened when this key K1 is on, when this K1 key is on, then what happened, this inductor is out of circuit, and so it will be charging this capacitor, as the circuit is completed here. Only when K1 is closed, then what happened, this capacitor will be fully charged, and this side it will be positive and this side will be negative charge, will be attached onto this plate of the capacitor here as it is here. And now what happened, when it is fully charged, then this K1 will be put off. Okay, it will be put off, and then it will be put on with this K2. So when K2 is closed, then what happened, the fully charged capacitor, the current will try to discharge it, okay, through this part, okay, through this inductor, and it will be going on discharging, okay, discharging, charging, discharging, charging, like that. It will go keep on oscillating like this. That is why we call it this as LC oscillation, and in some textbook it may be seen as LC tank oscillation, because just like in the tank water flows inside it, okay, just like that, in that way it is also oscillating. Got it? Yes. Now let's try to see the different, okay, processes that takes place during such type of oscillation. Now we may divide it, the whole process of charging and discharging in one side and then reversing back again, okay, to and fro. That may take, okay, within some certain period of time, and that time period taken, let's take it as capital T. What is this time period? Time period capital T is nothing, it is a time taken to oscillate, okay, from, that means to oscillate means the flow of the charge or the current from one plate of the capacitor to the other plate through the inductor, and it again reversing back, okay, to the same plate through this through this inductor. That time we take it as what? Time period. Okay, that let that time period be denoted by capital T. Got it? So let's take it that at time t is equal to 0, at the very beginning when this capacitor is fully charged, and at that moment, okay, when this key is put on, that K2 is put on, let's take it that time as t equal to 0. In that case, what happened? Electric field energy, okay, the energy stored in the capacitor, let it be denoted by UE, okay, and that UE will be maximum. The expression of the energy stored in the case of what is this capacitor, I mean, that will be denoted by UE. U represent what? Your potential energy. So as it is stored in the form of electric field, okay, we call it this as field energy or electric field energy, or you can say potential energy stored in the capacitor as field energy, you can say. So that will be equal to what? Half CV square. What is this? Half CV square. This is nothing but the energy stored in the capacitor, and the C is what? C is nothing but the C is the capacitance of the capacitor, and your capital V is nothing but this is the instantaneous potential difference between the two plates of the capacitor. Okay, and if this potential difference at the very beginning, that will be the peak value of the potential, or you can say the maximum potential difference. In that case, it will be represented by what? Half C V naught square. So what will be this value? This will be the maximum value of the potential energy stored in the capacitor. Or you can also express this in another term as in terms of the charge stored in the parallel plates, on the parallel plates of the capacitor. If that instantaneous charge is denoted by Q, then it will be half Q square, and its maximum value or a peak value of the potential energy, we may call it that as UE max, that will be equal to half C Q naught square, where Q naught is nothing but this Q naught is the what? Total charge that is stored at the very beginning of this process onto the plate of the capacitor. Got it? Similarly, when this charge is discharging through the inductor, then what happens? Inductor will increase its what? Magnetic field, okay, and what happened? The energy stored in the inductor can be also related similar to like this. Before going further, let me tell you all about this, okay, then it will be better. So the potential energy stored in the case of that of the inductor in the form of magnetic field, that is denoted by UB. U represent for magnetic field, and capital B represents for that of magnetic induction or magnetic field induction. So the potential energy stored in the case of inductor, that will be denoted by UB, and this will be equal to what? Half L I square, where L is nothing but the inductance, okay, or inductance of this inductor, and I is nothing but this is I is the instantaneous current that is flowing through the inductor. Instantaneous current, I'm telling you, okay. So this will give you the instantaneous potential energy stored okay, in the inductor in the form of magnetic field. So its peak value will be equal to what, or maximum value, it will be equal to half L I naught square, like this. So this will be the peak or maximum value of what potential energy stored in the inductor in the form of magnetic field, okay, in the form of magnetic field. So what happened, this charging and discharging, okay, that is nothing but it is changing of energy, you can say in that way, also in another way, changing from the field energy to magnetic energy, okay, and is reversing back in that to and fro direction. So what happened in the first case, let's take it that the capacitor is fully charged, and after fully charging of this capacitor, let it be connected to the inductor, and the circuit diagram will be like this. So in this first case, what happened, your field energy in the capacitor, that will be maximum, and in the magnetic field energy stored in the inductor, that will be zero at the very beginning. So what happened, as I told you, that let's divide the whole process into some 8 parts, okay, 9 parts you can say, but the process will be of that of 8 part only, okay. So let's divide it the whole process into what, 8 parts, so that the time taken for the whole 8 part, let it be capital T. So let's divide it the whole process into what, 8 parts, so that after a time of t is equal to, small t is equal to capital T by 8, okay, small t is equal to capital T by 8, what happened, this current start discharging, okay, the charge that is totally stored in the capacitor start discharging, and the path of the current will be from capacitor to inductor along this path, as it is shown here. So at this time t is equal to capital T by 8, what happened, some amount of charge has been discharged through the inductor, and you will see that the field lines energy that is there, okay, this become less. On the other hand, no magnetic field lines which was there, it will be developing some field lines here like this. Can you see? So what happened, as the number of field lines decreases here in the inside the capacitor, that means in between the two parallel plates, what happened, magnetic field energy will be again generated. Why? Because current start increasing. Got it? And now see, in this case, let's take it that the field energy, okay, which was maximum here inside the capacitor, it decreases, and on the other hand, the field energy which was zero inside the inductor, the magnetic field energy which was zero there in the inductor, will now increases. So one decreases, another increases, but the total energy will remain same. That is a conservation of energy, okay. And now let's see for the third one, that means at a time t is equal to twice t by 8. As I told you that let's divide the whole process into 8 parts, and at this first 1 by 8 of this total time period capital T, this was happen, and in the next twice t by 8, okay, t is equal to twice capital T by 8, or you can say t by 4, okay. If you divide it to this, it will be equal to capital T by 4, right? So at this twice of t by 8, what happened, your energy inside the capacitor, that means your field energy, electric field energy inside the capacitor, it will be totally discharge, and so its field energy will be equal to 0. But on the other hand, what happened, the magnetic field energy, that will be maximum inside the in the inductor, okay. Now just like this, in the next part, that will be at time t is equal to thrice t by 8, okay, these two are equal. Got it? The magnetic field energy, that will be this magnetic field energy will decrease from maximum, and what happened, some energy will be also developed in the what capacitor. That means this is taking place of the charging of the capacitor, so current will be flowing through it again, okay, and charging of the capacitor takes place. In that case, what happened, the field energy, electric field energy stored in the capacitor will be equal to that energy, magnetic field energy stored in the what, inductor, right? like this is the process that takes place. So what happened, it will keep on charging, okay, and what happened, this capacitor will be fully charged again, okay, and there will not be no magnetic field energy stored in the inductor. So at t is equal to 4t by 8, okay, 4t by 8, that means this will be t by 2, that means half of the process will be completed here. That means whole of the charge which was positive there on the upper plate of the capacitor, that will be wholly discharged, and the whole positive charge again it will be coming here onto the lower plate of the parallel plate capacitor. It is done like this, okay. In that case, what happened, this electric field energy will be again what, maximum, and the magnetic field energy in the inductor, that will be equal to 0. That means this is just the reverse. See here, electric field energy in the capacitor it was maximum, magnetic field energy in the inductor it was 0, but these two changes, okay, magnetic field energy is equal to 0 here, and electric field energy is maximum, but the change in the electric field takes place. The electric field was downward, that means from positive plate, upper plate, to the negative plate. Here the positive plate is on the lower side and the electric field energy will be upward, okay. So what happened at this half of the time period, what happened, electric field energy is maximum, magnetic field is again 0. That means this process is again coming, but the only difference is that electric field is just opposite, okay. So now this side is at higher potential and that side will be at lower potential. In the next again 5t by 8 at a time, 5t by 8, what happened, it will again discharging takes place from this positive plate. Now you see that from this, okay, process, the current will be flowing in the same direction, okay, from capacitor to the inductor, okay, in the upper side. Got it? Now here it will start discharging the current in the opposite direction, okay. So what happened, from this capacitor that was fully charged, discharging will take place through this part, through the inductor, okay. And what happened, this magnetic field and what, electric field energy, that will be changing as per shown here. That means somehow the electric field energy from this maximum inside the capacitor it will decrease, but the same decrease in the energy will again what, develop in the form of magnetic field energy onto this inductor. So field energy decreases from here as due to the current flow. What happened, the magnetic field energy will again increase, okay, inside the inductor, and at this t is equal to 5t by 8, let's take it that the energy, okay, stored in the capacitor is equal to the magnetic field energy stored in the inductor. Likewise, what happened, this will keep on discharging from the capacitor to the inductor, and at t is equal to 6 capital T by 8, your field energy inside the capacitor it will be totally equal to 0, but there will be full magnetic energy stored inside the inductor. That means UB equal to maximum. And so what happened in the next step, that means T is equal to 7T by 8, what happened, the magnetic field energy will try to what, give the energy for charging of the capacitor. So what happened at this 7T by 8, your electric field energy stored in the capacitor is equal to the potential, magnetic potential energy stored in the inductor. At last, what happened, this will be fully charged, there will not be no magnetic field energy in the inductor, and the maximum what, electric field energy, okay, will be stored in the capacitor like this. So the same phenomenon comes here, okay. It goes from this capacitor, the charging, the direction of the current will be like this, and it will be charging again at this point. Now from this point again it will be discharging back again, and it gives you the same that is at the very beginning. So this completes the whole cycle, okay. This process of what, oscillating the current from to and fro, that means from the positive plate to the negative plate, and from this it will be positive again and back again to that plate of the capacitor, okay, through the inductor. That process we call it as what? LC oscillation. And this LC oscillation, now the oscillation may be of two types, okay. The first one is what? Undamped oscillation, and the second one may be damped oscillation. So this damped oscillation, I will tell you about the damped oscillation first. If the amplitude, okay, if the amplitude of oscillations decreases with time, okay, then that type of oscillation we call it as damped oscillation. That is happening here. Got it? Suppose if you meant to vibrate a loaded spring, and if you keep on observing for say some for longer time, then what happen? The oscillation will keep on what? Having decreasing its amplitude with time. So after what? For some time, say after 1 hour or so, what happen? If you observe it, then what happen? Its amplitude will keep on decreasing, and then what happen? Ultimately it will stop vibration or oscillation. Got it? So such type of oscillation in which the amplitude of the oscillation decreases with time, that type of oscillation we call it as damped oscillations, and it is of no much importance in the practical application. So we want to have undamped oscillation. What is meant by undamped oscillations? Amplitude of the oscillation or vibration, if it is what? Practically what? Remains constant, okay, with time, then what happened? That type of oscillation we call it as undamped oscillations. That means amplitude will remain constant with time, okay. So that type of oscillations we call it as undamped oscillations. And whatever we have discussed, that LC oscillation is nothing but that is undamped oscillator, okay. So such type of LC oscillators are used in the case of what? Your transmitters. It may be radio transmitter, TV transmitter, wireless transmitter, and even it is used inside your own mobile, okay. So such type of LC oscillator we may call it as tank oscillator circuit also. Now if in that LC oscillation, if you connect it one antenna, okay, from here, then what happen? That antenna will try to emit, okay, those signals, okay, of these oscillations. I will tell you with equations, okay, in the next slide. Now let's take it that if Q be the charge on the capacitor at any time, that means the instantaneous charge, you may call it this as instantaneous charge, and this small q be the instantaneous charge onto the plate of a capacitor at any time, say let's take it as small t, and di by dt, that means differentiation of the current with respect to time, right? So di by dt be the rate of change of current. Then what happened? We know that just to have that what LC oscillations, I told you that the what induced EMF that is developed in the inductor will be equal to the potential difference that is developed what inside the capacitor onto the plates of the capacitor. So what happened when this is the induced EMF and this is the potential difference across the capacitor, then what happened when these two are equal, then what happened? That flow of or oscillation of charge is oscillation of the current is possible. Got it? So as there is no source of EMF other than these two components, what happened? The induced EMF, okay, the induced EMF and the what potential drop across the what capacitor, the sum of these two will be equal to 0, okay. You may use your Kirchhoff's what voltage law, or you can call it this as Kirchhoff's second law, or you may call it as loop rule, right? So if you apply it also, it will be equal to 0 as there is no source of EMF, right? So what happened when this di by dt, now let me show you, okay. Now let me use it, this one. So what happened? This L di by dt, L di by dt, okay, let me write it here, di by dt, this will be equal to what? L di by dt, we know that d by dt of I, right? But this I, current, we know that current may be defined as rate of flow of charge. So instead of this I, you take it as dq by dt. So what happened? This will be equal to what? The double differentiation of what? The charge. So d square q divided by dt square. We can write it like this. So that is what I'm doing here. So double differentiation of charge plus your this q by LC. If you divide the whole, okay, terms of this equation by L, then what happen? It will be in the denominator, it will be what? LC will be equal to 0 like this. But this LC, okay, this is nothing but this will be equal to omega square. Okay, let's represent it by omega square. Why? Because in resonance, that one omega, okay, will be equal to what? Root over of what? LC. 1 by LC, like that. Got it? When omega R is equal to omega C, that is nothing but actually that is your resonance. When what happen? XL is equal to XC, resonance takes place, right? So that means if you are trying to express it with that of angular frequency like that, omega R will be equal to omega RL will be equal to XL. That means your inductive reactance and your capacitive reactance XC will be equal to what? Omega RC, like this. So if your omega R square will be equal to what? 1 by LC. So your omega R, okay, that will be equal to what? 1 by root over LC. Am I right? So that is what we are using it. Okay, so that is what we are using it. Omega R will be equal to what? 1 by of what? Root over of LC. That is what I'm using here. So this is in the form of that one d square, okay, q by dt square plus omega square q is equal to 0. So this is just the simple harmonic equation that we have learned in class 11. Okay, that will be equal to what? Your d square x divided by dt square, okay, plus your this one omega square x, this will be equal to 0. This equation is nothing but this is the equation of simple harmonic oscillation, okay, SHO, simple harmonic motion. If it is of simple harmonic motion, then the equation, the general equation of simple harmonic motion will be equal to like this. So this equation is very much similar to that equation that we have just discussed now. That is what? Your d square q by dt square, this will not equal to, this will be plus, okay, what? 1 by LCQ, right? So instead of this 1 by LCQ, we just represent it by what? Omega square x. Okay, so this 1 by LC will be equal to what? Omega square. So this is of the form of this one, right? So what happened? Your angular frequency, okay, omega will be equal to what? Your omega will be equal to 1 by root over of LC, like this. Clear? That is what we are having here. Okay, so this is of the form of simple harmonic equation, and so this what will represent the oscillation, what is called as undamped oscillation. It will keep on oscillating. So the final equation represents what? The simple harmonic what? Oscillator, or rather you can call it as simple harmonic electrical oscillation with what? Omega as angular frequency, and your omega will be equal to what? 1 by root over of LC. So omega, we know that that is equal to what? Twice pi by t, twice pi by t. That means your omega will be equal to what? Twice pi by t. So let me write somewhere here, twice pi by t. So twice pi by t means what? It will be equal to twice pi of 1 by t. It will be what? F, right? So your F can be expressed as what? Twice pi f will be equal to what? 1 by root over of LC. So if you want to express it f, then what happened? Twice pi need to go downward to the denominator, so that it will be equal to what? 1 by twice pi root over of LC. Got it? So like this. Clear? So this is all about that of what? The LC oscillation. Actually in your syllabus, your LC oscillation should be deal only with the qualitative ideas, but we have done with the frequencies and all this expression. Let it be okay. This is for your, from the examination point of view, you need to know all these frequencies, angular frequencies, the expressions of simple harmonic motions and all. Okay, now let's go to that of what? SE generator. Okay, now this is the cross-sectional diagram of the SE generator. In it, what happened? There will be two cylindrical pole pieces. One is north, another is south, like this, north south. The magnetic field will be from north to south. And why we are having this radial, why we are having this cylindrical pole pieces? Just so as to have that radial magnetic field. Why radial magnetic field is required? So as to produce that maximum current. Okay, and that means when the direction of the magnetic field and the direction or the plane of the coil, if they are perpendicular, then what happen? Maximum what? Torque is produced. So if that maximum torque is produced, naturally the current produced, okay, due to the rotation of the rectangular coil placed inside the magnetic field, that will be maximum. So this is the circuit or the cross-sectional diagram or circuit diagram, you can say, of that of what? AC generator. AC generator may be called as also as AC dynamo, okay, or alternator. Why? Because in the case of AC, the the direction of the current will changes after a definite interval of time. Okay, as per definition, what happen? AC current is that type of current which changes its magnitude continuously and reverses its direction periodically, right? So this is nothing but this is the cross-sectional diagram of the AC generator. And AC generator is that generator which converts the mechanical energy into electrical energy, and this type of electric current that is produced by this generator is AC. So we call it this type of generator as AC generator. There is also another type what we call as DC generator. Okay, that one is not included in your syllabus, we have already done in class 10. Okay, now at the first half, let's take it that the coil, rectangular coil, there will be large number of turns rectangular coils. Okay, not only a single rectangular coil, actually there are large number of such rectangular coils, okay, wound onto that armature, right? It will not be shown here. So for the what studying purpose or learning purpose, let's take it that there is having a rectangular coil like this. Okay, and let the coil be represented by PQRS like this. Okay, and these blue colors, these are nothing but these are the rings. What rings? We call it these as slip rings, SLIP. Okay, R1 and R2 are slip rings. This blue in color, this denoted by B1 and B2, these are nothing but these are the brushes. Okay, we call it this as carbon brushes. Okay, and these carbon brushes will always be met contact with these slip rings, so that what happen? There will be a what connection. Okay, connection between what and what? This slip ring and the brush, so that what happen? Current can flow easily whenever this armature is also rotated. Okay, when armature is rotated, what happen? This slip ring will also rotated with it, but this brush will always made in contact, so that there will be always an electrical connection in between the slip ring and these brushes, so that what happen, the current can be taken out from these what two terminals across this load resistor. Okay, so one will be connected from here, another will be connected here. Okay, so that will be the output of the AC generator, right? So this is the, let's take it that this is the first half of the what the oscillation or the cycle of the rotation of this rectangular coil PQRS. But in the next half, what happened, P will be coming on this side as it is like this, S will be on this side. Okay, so what happened, P and Q will come on this side of the north pole, which was there on the south pole, on the side of the south pole, now come to the north pole, and then your R and S, which is now in the north pole side, it will go to that of the what south pole side. Okay, so what happened, this is the first half and this is the second half. When it completes again the second half, it will come again to its initial stage like this. So what happened, the rectangular coil will keep on rotating inside the magnetic field. We know that when current carrying when conductor is rotating or moving inside the magnetic field, it will produce or generate current onto that conductor. This is a reverse process of that of what, that when a magnetic when a current carrying conductor placed inside a magnetic field, okay, then what happened, it experience a force, right? So force is given onto this conductor inside the magnetic field, and then current will be generated in it. Okay, that is the process. So let's take it that what are the components that are what necessary for this AC generator. So let's try to see first the principle of AC generator. What is the principle of AC generator? The principle of AC generator is nothing but this is EMI, that means electromagnetic induction. Electromagnetic induction is the principle of AC generator. Or you can also say that when a current when a conductor placed inside the magnetic field, if it moves, okay, when a conductor inside the magnetic field moves, then what happen, it produces what, or induces electric current in it. Okay, you can also say that this is just the phenomenon of what your what motional EMF. When a conductor is moved inside the magnetic field, what happen, induced EMF is developed in it. Okay, you can give like this simply as electromagnetic induction, or as like this principle of AC generator is that when conductor is moved inside the magnetic field, induced EMF is developed in it. So for the construction of AC generator, what are the components that are required? Okay, the first one is what, strong cylindrical or radial pole pieces. Second one is armature or that rectangular coil, which was denoted by PQRS. The slip rings with the blue color denoted by R1 and R2 in that previous diagram. Okay, that is the slip rings. And the what, that with deep blue one, brushes B1 and B2, okay, which are connected to that. Okay, the external resistance, we call it that high external resistance as lot resistance, and so that is denoted by what, by lot. Okay, we call it that as lot. Okay, the external high resistance through across which the output is taken out, we call it that as load. So for the working of this AC generator, let's take that the armature is rotated in such a way that the arm PQ goes down. Okay, you just try to what reverse backward the video and try to observe that diagram. Okay, so in that I can show you what happened. This arm PQ goes down and your RS comes up from the plane of the diagram. So induced EMF will be develop or set up in the coil by applying your Fleming's right hand rule or generator rule. The direction of the current will be what? PQ, RS, R2, B2, B1, R1, P, like that. That is what we have just seen. Okay, so what happened when this PQ is moving downward, and then what happened, your RS, okay, will come upward. Then what happened, the induced EMF by applying your Fleming right hand rule with the direction of the current will be what? PQRS, then what? R1, B1, then it will go through the lot, then it will be B2, R2, then it will be moving in the I'm sorry, the direction of the current, induced current, will be from P, Q, R, S, and this N is connected not to R1. I thought that it was an R1, so it will be what? Connected to this R2, B2, then it will go like this, the current, then B1, R1, then P again. So that is the process of the in the direction of the induced EMF. Okay, it will go like this. Got it? The direction of the current will be in this direction. So what? P, Q, R, S, then R2, B2, B1, R1, and then coming back to P again. So it completes the loop, right? In this way. Got it? So this is in the first half. In the second half, what happened after the half rotation of the coil PQ comes up, your PQ will comes up, and then what happened, your side of the coil, what happened, RS will go down. Okay, so again, by applying the Fleming right hand rule, which is also known as generator rule, the direction of the current will be what? P R1. Okay, it will go like this, P R1, then what happened, R1, P is always connected to R1, right? So P R1, B1, then B2, R2, then S, R, Q, P, like that. Got it? So the direction of the current in that first half and the second half, the direction of the current is just opposite. In that first half, the direction of the current goes from where to where? From B2 to B1. But in the second half, the direction of the current is from B1 to B2. So for every half rotation, what happened? The direction of the current will be what? Changing its direction. That is what we call as alternating current. Got it? So in one way of the current is taken positive, then the reverse current is taken negative. So if you take it that the first direction of the current from B2 to B1, if you take it that as positive, then B2 to B1 you have to take it that as negative. Okay, therefore the direction of the current what changes periodically after every half of a time period. Okay, therefore the current is said to be what? Alternating, and the corresponding wave is sinusoidal. The sinusoidal waveform is shown here like this. Got it? Now for the theory, let's take it that the magnetic field, okay, link with that rectangular coil, let's take it that as phi. Got it? And what is this capital N? Capital N is a total number of the turns of the rectangular coil, that is denoted by N. What is this B? B is the magnetic field that is produced by the cylindrical pole pieces. A, the area of the rectangular coil, and theta is nothing but this is the angle between the normal to the rectangular coil area, normal to the area of the rectangular coil max with the magnetic field. Okay, so your phi, actually phi is denoted by BA, right? Phi is denoted by what? Phi is denoted by B dot A. We have done this one. So if there are some n turns, for one turn this will be the expression, but if there are capital N number of turns, then you need to put that factor n. If there are 2 turns, then twice of this. If there are 3 turns, 3 times of this B dot A. If there are capital N number of turns, then you need to put a factor capital N here like this, n times. Okay, so if the angle between this magnetic field B here and the normal to the area, okay, that will give you the area vector, right? So if the angle between this magnetic field B and the area vector, if it is denoted by theta, then what happen? B dot A will be what? This will be equal to n times of B A cosine of that angle theta. Now this angle theta changes with the rotation of this what? Armature or rectangular coil, okay? And if that rotation of this rectangular coil with some angular frequency omega, then we can replace it this theta by omega t, so that we can have what? Just like this, nba cosine of omega t. Instead of theta you will have omega t. Got it? So differentiate, this is nothing but this is the total magnetic flux at any instant, okay, onto this area of the rectangular coil. So differentiating this, what? D phi by dt we will have, okay, d phi by dt, and cosine of differentiation of cosine of omega t, we know that it is minus omega t, okay, minus sine of omega t, okay. And after differentiation of this sine, we need to differentiate each angle again. For that differentiation another omega will come up, so differentiation of d phi by dt will be equal to minus nba omega sine of omega t. Now we know that induced EMF is equal to minus d phi by dt, right, from your Faraday's laws of electromagnetic induction, right? And this minus will be what? Due to that of Lenz's law. Okay, so with this minus and this minus, if you try to replace it, then it will come plus, and your induced EMF will be equal to what? nba omega sine of omega t, like this. So what is this? This is the instantaneous induced EMF, okay, and this induced EMF will be what? Obtained onto that output, right? So what happen if you have that E is equal to this? These are all constant, n b a omega, okay. As long as you are not speeding up or slowing down of that rotation, then what happen? Your angular velocity omega will be also constant. So all these are constant, and let's denote it these as what? E naught, where E naught is the peak value of the EMF. Okay, so this peak value, then you can represent it, your instantaneous EMF E is equal to E naught sine of omega t. This is the instantaneous EMF of AC, right? And moreover it is also sinusoidal, and so the sinusoidal function can represent alternating current. We have already learned about that one, okay, and that one can, your EMF can be represented like this. So up to here, this is for the one complete oscillation. Half of the oscillation is on the positive side, on in the second half it will be on the opposite side, and that opposite side is taken as what? Negative. If you take it this side as positive, then the other side will be taken as negative. So it completes one oscillation, and if you keep on rotating, then what happen? It will be giving you this alternating current, okay, as long as you are having that what? Rotation of the rectangular coil, right? So with that we come to the end of the today's topic. In the next what video we will try to cover up that of the transformer, okay. Let's try to wind it up with this. Thank you for watching my video.